Okay, yeah. So my name is Anurag Gupta, as Shakti just introduced, and I'll be briefly talking about a particular discipline of courses that we offer in mechanical engineering, and some of you might be teaching some of these courses. Strength of materials. Are there anyone? Is there anyone who teaches strength of materials or mechanics of solids? Or yeah. Okay. Yeah. And I'm sure you all must have learned these things in your undergraduate. So what we do is here is, and I'll talk about the importance of these courses as I go into it. The first course that we teach here, so we don't have a engineering mechanics course here. Many places have a course called engineering mechanics, usually in the first year, where they talk about statics. Force balance and simple structures. We don't have a statics course here. We don't have an engineering mechanics course. We right away have a course called mechanics of solids, and the statics are also covered in this course very briefly. But in general, what is the attempt is to try to introduce student to the mechanics of deformable solids which are deformable. This is in contrast to rigid body dynamics. So of course there is a course which is offered in the second year when this course is also offered. So this course is taken in the second year by undergraduate students. So there is a course on dynamics. Now this course on dynamics deals with bodies which are treated as rigid bodies. On the other hand, in this course we are looking at bodies which are treated as deformable bodies. Okay, so that is the main distinction, and many of you might know from your experience that it's a very important subject to learn for design purposes. For one thing, anything that you see around, you want to design this table, this building that you see, the chairs that you're sitting, all that needs you to understand how will these structures fail? How will these structures behave under external load, right? Will this chair that you're sitting be able to take your load? Okay, and it has to take your load. It doesn't have to have a size of elephant sitting on this chair, right? We don't need to design this chair for elephant. We need to design this chair for humans. So there is a prescribed load under which this chair doesn't have to fail. So how do I ensure that? Okay, so the central ideas behind this designing, which goes on in other, which is sort of taught in other courses, the methodology of design, but the core fundamental ideas are this notion of stresses and strains. The idea of stress sort of is at the core of the idea of failure, the idea of lifetime of a structure, the idea of strength of a structure. Okay, and this course is primarily taught with that focus in mind, that it is the beginning of this series of courses in future, and therefore this course is taught to a broad variety of students. This is a compulsory course here for not just mechanical students, but also students from aerospace who also need similar design principles, civil engineering. Okay, in fact this discipline arose out of civil engineering, because it was initially the civil engineers who were interested in talking about strength of, even before machines came into being, they were interested in designing stronger bridges, stronger buildings which could sort of live for long times. And also material science department also, because they're often into practices of calculating material properties. So it is important to know about mechanics of materials, to know about material properties. Beside these departments, there are always students from other departments, often like physics, maths, chemical engineering, who drop by to take this course. But otherwise, it is compulsory for these four departments. We usually have 3 lectures every week for this course, and there is a tutorial where one solves a set of problems. Now something that I would like to emphasize, and it's a very, very important point, is the textbook that one chooses for this course. Now you have to understand and I cannot emphasize this more, that this is the first course in which the student is being exposed to certain very important fundamental notions, the notions that he will eventually use for his other courses in design, for advanced courses at postgraduate level, for many things if he wishes to build a career in science and engineering. So it is very important to introduce these fundamental ideas in the best possible manner, and therefore textbook, the choice of textbook is important, and usually it is a good idea to take a textbook which has been internationally proven to be a good textbook for the course. So there are a couple of such textbooks. I mean, what I have mentioned here is the one that is used at IIT Kanpur. It's being used consistently at IIT Kanpur for several years, if not more, if not several decades. It's a very well written book, but you can also go for, there's another book by Prof, which is very popular. Then there is a book by Timoshenko that some of you might have seen. There are also several books by Indian authors, and some of them might be good, but some of them have been written just at the request of publishers and just to sort of they just collect material and write a book. Okay, so the books might, so there could be a set of books which might look more accessible to you, but just by that virtue you should not choose a book. Choice of book is very important, because this is what students also take away with them. Okay, so always be very particular about choice of books. Having said this, let me also just briefly go through what all we teach in this course. You can get this information also from our website, but just a brief overview just to tell you how much we cover. We used to cover much more in this course, but past couple of years there has been a revision and we have sort of reduced the course content. So essentially we start with statics, as I mentioned, and we start talking about the important concept of free body diagram, which student has to understand well. Now, as I said, that in certain places there are whole courses called engineering mechanics, where the whole course is about free body diagrams and things like that. But here we just have this notion. In this portion of statics, in particular, the important aspects are introduction of concepts of force, displacement, equilibrium, compatibility, right? The important difference between statically determinate structures. Statically determinate structures are those where forces in the structure can be obtained only by equilibrium equations. Statically indeterminate structures are those where forces in the structure cannot be obtained purely by equilibrium equations. You have to also bring in material, some kind of constitutive law, Hooke's law for example. So this is how one starts, and with this motivation one starts to talk about the concept of stress at a point in a body. Okay, and we talk about a lot of associated notions. There should be principal stresses here. We talk about principal stresses. We talk about how stress components are transformed under coordinate transformation. We talk about the idea of Mohr circle. The Mohr circle is very important to visualize how stress gets transformed. We talk about notions like von Mises stress, notion which is important. I mean, it's a very basic notion, but sort of the most elementary way to start talking about failure and strength of solids. So then we talk about concept of strain. Strain is essentially something which tells you how the body is deforming. So a rigid body does not have any strain, but a deformable body is defined by the notion that it has strain. We talk about principal strains, Mohr circle again for the strain, and we also talk about certain ways of measuring strains experimentally. I'll come to that. In a follow-up course, we do some experiments with strain rosette, where we experimentally measure these strains. Then we talk about stress-strain relationship. It's a very important notion, because when you have equilibrium on one hand and strain on the other hand. So strain is a notion which is connected to displacement, which is a geometric notion and which is associated with the deformation of the body. Stress on the other hand is a thermodynamic notion. It is associated with how the body is responding to the changes to the deformation in general, and it is this response. So for example, when I stand on this floor, when will this floor, so, and I asked this question that if I stand on this floor, will this floor break or not, right? I mean, this question doesn't often come in our mind, but it is an important question, right? I mean, we have these tall buildings and I can run on this floor above. And it is an important question to ask, how should I design this roof such that when I run on the floor above, it doesn't fall down, right? So that is where stress of what is happening as I am running through the floor is responding back by generating stresses, okay? And if the stresses are sufficient, I mean, like if they are within limits, then the floor will not fail. On the other hand, if an elephant is running on the floor above, then the stresses which will generate in the floor will be higher than the permissible stresses, and the floor will fail. As, I mean, very simply put, I mean, this is more complicated than what I just said, but the basic idea is that, okay? So what these relationships kind of deal with is how geometric notions are related with thermodynamic notions, and this depends on the material at hand, okay? The way, for the same strain, how a rubber-like material will behave will be very different from a steel-like material will behave. Okay, so these things are captured in stress-strain relationships. You are probably aware of Hooke's law kind of relations, which are stress-strain relationships. We also talk about more advanced material behaviors like plasticity. We talk about when the material behavior could be rate dependent or rate independent, which means, see, you can load, I can sit on this table very slowly. On the other hand, I can start jumping on this table. Okay, the way this table behave will be very different. You understand? See, if I sit on this table very slowly, or a little kid of much lower weight than I have starts jumping on the table, then it could happen that because of the jumping of that kid, this table might fail. So the response of the body depends very strongly to the way the load has been applied, right? So these are important notions, okay? And the same body can behave in a rate independent manner, in a rate dependent manner. It can behave plastically, okay? It can behave in a viscoplastic manner, okay? So there is a whole array of material behavior which one needs to talk about. One can talk about strain hardening, which appears in during plasticity, and a very important subject of fracture, okay? When could fracture start to appear, and if it has started, how would it propagate? Of course, we don't go into details of these. We have separate courses on each of these topics, almost each of these topics at our postgraduate level, which a lot of our undergraduate students also take in their later years if they are interested. This is even more reason why this course is so important, because this is the first course where the students are getting inducted in such a area, okay, which is very broad and which is very rich in terms of course material. So it is very important that this course is taught well, so as to generate interest, so as to prepare the student well, and so as to make him interested in these important notions. We also talk briefly about slender structures, like not briefly actually, this is something we talk in detail, bending of beams, how stresses develop during bending of beams, how stresses are developed during torsion of usually shafts with circular cross section. Okay, so this is one course that students take in the second year, and as I said that it is a compulsory course for several departments, the ones I mentioned. But then we have a course in a compulsory course for mechanical engineering students, not for other departments, which is called Advanced Mechanics of Solids, which essentially builds up on the previous course, but takes a more matured viewpoint towards the subject. And the emphasis in this course is to start exposing students to pose realistic problems. How can they pose realistic boundary value problems? Okay, how can they write, how can they go systematically towards, let's say they are finally going to solve a problem using some FEM code, finite element code, which is what many people do in industry, for example, right? But just rather than using a FEM code as a black box without knowing, without knowing what is going on in the code, to actually know what the code is doing, although you're still using the code as a black box, but to know what is going on in the code, it is always more beneficial. So what this course sort of attempts to do is to provide the students more detailed knowledge about the course material, and like as I said, the emphasis is on formulating boundary value problems and how these boundary value problems can be solved. So of course, what we talk about in this course is to solve some simple boundary value problems, but these simple boundary value problems can be the benchmark problems against which you can test a code. See, you can't, let's say you have to design the chair, as I mentioned, against a certain load. I mean, you're not going to go and start working in your finite element program for the chair. I mean, you will first want to see whether the way you are doing it is correct or not. So you will first try to play around with simple problems, right? And you would want to verify whether what you have obtained is correct or not. So that's why you will always want to have certain benchmark problems whose solutions are known otherwise. Okay, so it's very important to know about some of these benchmark problems. Also, analytical solutions are important because they give you certain insights about the problem, which a numerical solution can never give you. So these things go in hand in hand. So we expose the students on various solution methodologies, okay, with which the problem can be solved. We supplement this course with a lab component. So what we have is we have 2 lectures every week, and we have a lab component. So we have a lab every week, and I'll show you what kind of experiments students do. I mean, they essentially are exposed to basic techniques of measuring stresses and strains, right? Essentially strains, and then stresses are derived from strains using some constitutive law. And as I said, and this course essentially is a starting point for advanced courses in solid mechanics, which we offer in plenty. And it has been often seen that this is the course which actually always generates special interest in a small fraction of students who end up taking this subject as a subject of their interest in future studies and future expertise. And again, as I mentioned before, the choice of textbook again is very important, but contrary to the previous course, which is a very well established course around the world, and therefore there are proper textbooks associated with mechanics of solids, there is, like, it's very difficult to find a intermediary level textbook, because as I said, this course is a kind of bridge between that elementary course that we taught and more advanced courses. Okay, so somehow the language is also intermediary, and it is very difficult to find a book which sort of deals in this way. But there are a couple of books that we sort of use, and they're good books. This book by Bauer, Applied Mechanics of Solids. The good thing about this book is it is fairly new. It's a very detailed book, and the author has also made the whole book online. So this book is present online, so the students can refer to it. It has a wealth of problems. It is very detailed. It covers a vast variety of topics also. So it gives the student a decent amount of exposure. Then there are certain other books, like this book by Saad, who talks about elasticity. Just very briefly on what we cover in this course usually. Unlike the previous course where the emphasis is more on general concepts, just brief notions, here we teach the course to the students in a more formal manner, the way we usually teach solid mechanics courses at a graduate level. So we start by building certain mathematical preliminaries which are required for the course. In particular, we start talking about the notions of vectors and tensors, some notions from linear algebra that a student is already exposed to in some sense in its math courses. So he's sort of excited to see some of that math curriculum being used. And also it is important to emphasize to the students that the natural way to start building a physical theory is to start talking about concepts of vectors and tensors, because it is these notions of vectors and tensors which lead to a coordinate independent theory. I mean, you can't write physical law in terms of quantities which depend on a choice of coordinate system. Okay, so that's why vectors and tensors are important. We revisit the notion of strain and stress, but in a more rigorous manner, in a more formal manner, and we differentiate between small strain and a small deformation. Stress, we talk about Cauchy stress, we talk about equilibrium of stress, we again talk about principal stresses. In particular, we spend a lot of time in talking about boundary value problems in linear thermoelasticity, where you have a body where you assume that the strains are not very large, and it can be also exposed to a thermal environment. We usually look at a decoupled problem, and in this concept, in this context, we look at these important notions of superposition, because the problem is linear. So you can sort of separate problems in separate parts and add them up. So it's a very important notion. And we also talk about uniqueness of the solution. This is also an important notion, because many times we solve a semi-inverse problem. So we sort of guess a solution. So if we are confident about the uniqueness of the solution, then if anyhow we are able to construct a solution, then we know that that solution is unique. Okay, so the uniqueness is also a very important aspect of the problem. So we spend a lot of time on sort of establishing these notions, and then we visit lots of simple problems within the settings of plane stress, plane strain, axisymmetry. I mean, these are just some simplified notions rather than working in the full three-dimensional settings. And in terms of problems, more specific problems, we try to work out problems in contact mechanics. Important, I mean, contact is everywhere. You see contact of this remote control with the table and things like that. If I jump on this table, I'll have a contact with the table. Then crack, I mean, crack is important. I mean, you need to know the stress field around the crack tip to tell you whether this crack will propagate or not, or if it propagates, how fast it will propagate. Okay, important for understanding the strength of the solid. So, and some other problem. Here we also visit torsion of non-circular cross sections. Okay. And we talk about energy methods. This is the important point of departure, because as I said, it is with this point of departure, the student can feel comfortable with advanced courses. I should also mention that we have advanced courses in finite elements also. We have several courses at graduate level on finite element method. And this course provides a very natural passage towards those advanced courses in finite element method. So that's the thing. Just very briefly, let me show you what lab sessions are. So, I mean, all these are strain measurements using either strain gauge techniques, which are more mechanical, or there are these optical techniques, photoelasticity or DIC, which are more optical techniques of measuring strains. Okay. Sometimes we also have a lab session where we expose student to a commercial finite element software like Abacus, and we sort of expose him to how to solve a more realistic, more complicated problem. Okay, so that's it. Yeah. So this is how we sort of expose our students in undergraduate program to these subjects. Okay, thank you. So I'll be happy to take any questions here.